Let's look at reference electrodes. Now, so far we've been talking about standard potentials and we haven't really discussed where those came from. Why did we decide that, or what's the way that we orient ourselves? How do we know what value is which? Well, we had to make a choice on what we're going to measure each reaction against something, some reference. And we chose hydrogen as that reference. And we made an electrode that involves the reduction of H plus into H2 gas. And so let me just write the reaction right here. We have 2H plus plus 2 electrons goes to H2 gas. And we have just chosen that this reaction will have a voltage of 0, this reduction reaction, or a potential of 0. We'll draw a little line through there. Now, I've already drawn up what a standard hydrogen electrode looks like. I might not have used the name, but it uses a platinum wire because there's nothing here that I could clip an electrode to. I need some metallic substance to do that, and neither of these things are metallic. And then we have bubbled hydrogen gas around that electrode. It's the gas. And if it's under standard conditions and actually measuring at 0 volts, this would be 1 bar of pressure. And then we have another phase change here, and we'll have our H plus. That's aqueous. And this will have a concentration of 1 molar. Well, actually, it has an activity of 1, but really it's 1 molar concentration. And then we'll have our salt bridge. Now, this is called the standard hydrogen electrode. And it gets abbreviated SHE, or SHE. And we've arbitrarily chosen that that potential should be 0. And it does so happen that this is right about in the middle of our known substances. You might recall from a while back in a previous video that fluorine had a standard reduction potential of 2.866, and lithium had a standard reduction potential of negative 3.05. And so it is pretty much in the middle of those substances. And we tend to like to use hydrogen. It is the most abundant element in the universe, so we won't run out of it. We may run out of the platinum to use it, but that doesn't get used up during the reaction. So it's what we chose. Now, one of the reasons to make sure and choose something in the middle is so that in case we discovered some substance that had even more oxidizing power than fluorine, or even a better reducing agent than lithium, that we're not stuck with, oh, what do we do now when we have a negative number? So it's just best to pick something in the middle, and any other discoveries will just work themselves into the system, no problem. Now, some of you might be looking at this and saying, wow, we've got to have a platinum electrode. Those might be a little expensive. We need to have a fairly concentrated solution of acid, 1 molar. That will lead to a pH of 0, which is a pretty low pH. And we also have to have hydrogen gas. Now, hydrogen gas will have to come in a compressed cylinder, a large gas cylinder. And none of these things is particularly convenient, and it could be very difficult to make these small. So we've come up with a different electrode that will maintain a constant potential that we can use as a reference electrode. And we did use the standard hydrogen electrode to measure the potential of this one, but from then on, we can use this more convenient to use electrode. Now, there's two kinds of these that are typically used. There's a saturated calomel electrode, which is based on mercury and mercury chloride, but that one uses liquid mercury, and so it has its own issues. And then there's the silver chloride reference electrode. And this one gets used a lot more because silver is just a little bit easier to work with, and it's also not toxic, and it's not a liquid. So that makes it a little bit more convenient. And the reference electrode for that has a line notation that looks like this. We have silver metal with silver chloride, solid, and that has a solution of chloride ions in it. It will have some silver ions in it, but those are not important for the electrochemical reaction that we're actually measuring. And then we'll have our salt bridge. So what's the actual reaction that this is measuring? Well, it's the reduction of silver chloride to make silver metal and chloride ions. This is what it looks like. So we have silver chloride, we add an electron to it, we make silver metal, and then free chloride in the solution. Now you'll notice here that this is a solid and that's a solid. So the only thing in here that's a dissolved species is the chloride. Now, if we think back to the Nernst equation, we can see how this might be to our advantage. The Nernst equation for this reaction would be this. The standard reduction potential for this reaction is 0.222. And then same thing, log of, okay, now here's the reaction quotient for this reaction. Chloride ion, that's it. That's a solid, that's a solid. So, concentration of chloride. Now, how does this help us? Well, in this case, the only thing that can change the potential is the concentration of chloride. So, if we could find a way to keep this concentration at the same level, not changing no matter what we do, then we would have an electrode that will not change potentials. And that is a useful thing. Because if we just have a metallic wire, that can change potentials extremely quickly. And we have no way of knowing what the potential actually is. Well, we can measure it relative to some other potential that we do know. And that's where our reference electrode comes in. So we just need a way to keep the chloride concentration the same. And here's how you do it. Here's what a silver chloride reference electrode actually looks like. We have some tube here, and down at the bottom is our porous plug. That's our salt bridge. We'll need that so that we can use the electrode in some other solution. We can just have this all in one neat package and then dip the electrode in whatever solution we want to measure. And we'll have a silver wire. It's kind of in a little loop. And in the middle of this loop, we're going to pack in some silver chloride. Because these are both solids, they need to kind of be right next to each other in order for a reaction to happen. Now, how are we going to keep the concentration of chloride the same? Well, down here, we're going to put a whole bunch of potassium chloride. And there'll probably be some silver chloride down here too, just because, well, there's some up here and it might fall down. It doesn't really matter, but we'll have a little bit of silver chloride down here too. That is less important, but what is important is that this solution is going to become completely saturated with potassium chloride. This is a very soluble salt. The concentration of chloride in here is going to be quite high. And when that happens, we'll be able to maintain the concentration of chloride. So you might say, well, what happens if this reaction goes forward a little bit? What if we turn some of this silver chloride into silver metal, and then we generate some chloride ion? That would increase the concentration of chloride. Well, no, it actually can't, because everything that could possibly dissolve in here is dissolved. It's saturated. So if we generate any more of this, some will precipitate out. Had some trouble there. Now, conversely, if we do convert some of the silver metal into silver chloride, because we really don't know which direction this reaction could go. We could have the other reaction could be an oxidizing one, and that would turn this reaction backwards. Well, then we'd use up some of the chloride in solution to make silver chloride. Well, if we use some of it up, more of this potassium chloride will dissolve, replenish the chloride in solution, and maintain a constant concentration of chloride. And that's how a reference electrode works. Now, in the case of a saturated solution of chloride, this electrode actually has a potential of 0.197, and it will stay at that potential, assuming that you don't do wild things like run a lot of current through this electrode. It's not designed to run a lot of current through it. You only need to run a very little amount through in order to measure the potential. And as long as you're doing that, you won't wildly change the characteristics inside of this electrode, and you can determine what the potential is of something else, because you'll know this one is 0.197, and it will stay at that level constantly because we're keeping the chloride concentration the same, and so then this potential will stay the same.